Hey folks, Mrs. Sid here. We're going to do some work on inverses before I actually see you for inverses on Thursday. It's just to get us back on track with the other pre-calc classes. So hopefully I can get this done before the bell rings, but you might hear at the end of this video a little bit of a bell. So here we go. One-to-one functions help us with inverses because a function must be one-to-one in order to have an inverse function. So back in Algebra 1, Algebra 2, even with us, we talked a lot about if a thing is a function, whether it be a graph, table, mapping, formula, if it's a function, has to pass the vertical line test. You can think of one-to-one as it not only has to pass the vertical line test, but also it must pass the horizontal line test. So you see here in this first box, it has different ways to say it, but really thinking about it as a horizontal line test might be the best bet. So we really want functions to pass both line tests in order for them to have an inverse. And we're going to dig into inverses here. So we're going to figure out, are these functions one-to-one? So in part A, I see this definitely passes the vertical line test, but when I go to draw a horizontal line, I can see that this fails, and so this is not one-to-one. And I'm sad, but that means that to find the inverse of that, we would have to do a little bit of negotiating. We'll talk about that in a little bit. Okay, so how to spot this horizontal line test? Well, remember for a function, every x had to be unique. So it looks like every x is unique here. But we also, for it to pass the horizontal line test, need every y to be different. And if you notice right here, the 5s are the same. So we would say that this is not one-to-one. Okay, our last example here is a line. I know it's a line because that's y equals mx plus b. So if I would do like just a quick graph of that, it doesn't have to be anything special. Y-intercept is 5, slope is 2, so down 2 over 1. I'm kind of looking at something like this. Definitely passes vertical line test, horizontal line test. Yep, it passes. This is one-to-one, and this would be super friendly as an inverse. So that's just a little bit into one-to-one. And again, the reason we really like one-to-one is because then they give us an inverse function. So let's talk about how to find, once we say, okay, something is one-to-one, how do we find its inverse? So our first step, get a nice color here, our first step is to switch x and y. So where I see an x, I'm going to write y. Where I write a y, I'm going to write an x. After I switch x and y, I'm going to solve for y. And then my last step is to replace y with f inverse of x. So those are my 3 steps in finding the inverse. We're going to actually do a couple of these down below, just so you can see what in the heck does this look like. So the first thing I see is that, oh shoot, I don't really have a y, I have an f of x. So I'm just going to call this y equals negative 2/3 x plus 4. And now I'm really primed to do that next step. So I'm going to switch x and y. So I'm going to write x equals negative 3, negative 2/3 y plus 4. So notice that where I had an x is now a y, and where I had a y is now an x. So it definitely looks a little different. Now, unfortunately, I have that blank there for my answer. I'm going to have to kind of work around that. So my next step is going to be down here. I'm solving for y now, so the yellow bubble. So I'm going to subtract 4 from both sides. many of you are not fans of fractions. So what you can do first is multiply by 3. That gets rid of our denominator. And then you can divide by 2. So you get negative 3 over 2x plus 6 equals y. So our answer to the inverse, our formula, is going to be negative 3 halves x plus 6. So that's our inverse equation. So a line has a line that is its inverse. Right, part B gets a little bit trickier just because we have the cubing. But if you remember, just kind of give you a visual on this, our friend x cubed, granted this has been moved up 1 and horizontally, what is that, compressed or shrunk, it's roughly still looking like that. So passes vertical and horizontal line test, so we should be happy and good. All right, so let's go on to find the inverse. Now that we've convinced ourselves that this would have an inverse, I'm going to rewrite this as y equals, just so I have a clear y. And now I'm going to switch where I've written x, I'm going to write y, and where I write y, I'm going to write x. So same step. And now I have to solve for y. So again, I'm going to have to go behind this blank. So I'm going to subtract 1 from both sides. And then I'm going to cube root both sides. How wild is that? So I have a cube root of x minus 1 equals 2y. And now I have to divide everything by 2. So you can write that one of two ways. We can write this as 1/2 times the cube root of x minus 1. Or if you would prefer keeping it as some big fraction, you can. Those are the same things to me. So that's our inverse function. But the 3 steps above are really what I want you to know. Those are going to be important in doing these problems. Okay, by now you might think, oh, we're not doing any trig. Well, the goal of this unit is to get us to inverse trig. You can kind of see that up here in my title, inverse trig. So know that this trig is coming back. We're just taking a little momentary stop to talk about inverses. All right, so notice we have 2 lines there, and those look like the same 2 lines from 2a here. So we know they're inverses. We have them graphed. We have the blue and the red graph. So we're just going to use the graphs to get some... Sorry about that. That's the end of the day bell here at Northfield. So we're going to get the x-intercepts, all the intercepts, and then kind of talk about another point, and then kind of see if we can find a relationship here. All right, so x-intercept, actually it might be easier to start with the y-intercept, right? The y-intercept on the blue graph, is 4. I can see that from an equation. I can see that from the graph as well. The y-intercept for the red graph looks to be 6. I can see that again from the equation and from the graph. Okay, so let's look at x-intercept. Let's go back to the blue graph. Blue graph, the x-intercept looks like it's 6. And if I look at the red graph, its x-intercept is 4. Now, it's not a coincidence that we're getting the answers of 6 and 4 for both of these. But let's keep going. So let's find just a random point. It's just a third point. Let's see if I can find something along here that looks promising. This one looks not bad. So on the red line, it looks like I have the point 6, negative 3. Well, you might be already saying, I kind of know what that point is on the blue graph. And that's because maybe you see what's happening here, but when x is negative 3 for the blue graph, the y value is 6. Notice, just like we did algebraically, we're swapping x and y. It's kind of interesting, huh? If you're looking at that this way to this way, this way to this way, look at how these points all switch x and y. And that's what we did algebraically back here, remember? Step 1, switch x and y. So that's happening on the graph as well. Domain and range of these graphs is not exciting because they're lines. Domain is all real numbers, as is range. And then likewise here for domain and range. So much harder to see kind of that swapping back and forth with that. All right, so let's write down some interesting stuff that we just learned. Okay, so, there's also symmetry to this graph. I almost forgot before we write it down. You can see symmetry in this graph if I were to draw a line right here and fold along. I have the same on either side. This line, of course, you know the equation. It is y equals x. And so that's like a line of reflection. So let's talk about graphically what happens. Graphically, it's going to be what we just said. I'm going to say symmetric over the line y equals x. All right. If the function has a domain a comma b, where a and b are numbers, so like maybe it's -2 to 6, or -10 to 10, then that's going to be the range on the inverse function. And then likewise, if this range is c comma d, so maybe it's 3 comma 10, that would actually be the domain for the inverse. So again, we kind of get this x and y swapping, which is kind of interesting. All right, so let's talk about one last thing before we get into it. Let's switch this. It says, which means that a point, let's call it x comma y, on f of x becomes the point y comma x on f inverse. So x and y definitely switched. The reason I want to change that is because I used the a and the b already up here for the domain. Okay. And so just a couple more before we get to our final box and then wrap up this video. So these last ones, we want to do some composition. So it's been a while since we wrapped our heads around composition. So remember, this is saying do f of f inverse of 4. So you start with the inside and do f inverse of 4. So we have this graph, f inverse of 4. We'll remember that y coordinate is 0. So now we're going to do f of 0. And so f of 0 is just 4. So what I put in is exactly what I got out. Oh, that must be just a fluke. Let's check this out. Let's do f inverse of f of 6. Okay, so let's start with f of 6. F of 6 is, well, let me take a look at my graph again. So blue line, f of 6. Okay, so that's 0. So now this is going to be f inverse of 0. So red graph, f of 0. Wait a minute. This is 6. Do you see that, folks? Do you see that this is matching this? This is matching this? Okay, this has got to be unreal. All right, let's try this one more time and see if this is actually a thing. So f inverse of f of -6. Okay, so we start with f of -6. So let's go back up here. My f graph is the blue line. F of 6 is 0. hold on. Oh, -6. Oh, okay. So I was like, wait a minute, f of -6. So let's go -6. Okay, so that looks like 8. This has got to give us a different answer, right? Totally. Let's check it out. So f inverse of 8, I'm getting too excited here, I can barely write. F inverse of 8. So 8, F inverse is the red, and that is, okay, so that y coordinate is -6. Holy smokes. Check that out. It's the same again. Ah! Guess what, folks? That is a thing. It's part of this rule down here. Really, the definition of an inverse is that when you compose the inverses, whether you do F or G first or second doesn't really matter, but both compositions should get you X. And we will pick up with proving that they're inverses when I see you on Thursday. Remember, just by watching this video, you're going to get some points. See you Thursday.